Thank you for coming to spend part of your weekend here at the University of Auckland, and in particular at the Faculty of Engineering. It really is my pleasure and that of all of the team here that we work with to show you a little bit about our faculty and about what engineering has to offer. So my name is Rosalind Archer. I'm a professor in the faculty. I'm the head of the Department of Engineering Science, and I hold a research role sponsored by Mercury as a chair in geothermal energy. But I'm actually not going to say too much about geothermal. I'm here today to talk about the 2 degrees that we offer. So big theme, 1 department, 2 degrees. So the department is engineering science, and we offer 2 degrees, 1 in engineering science, 1 in biomedical engineering. And they are united really by this very simple flowchart. So what gets us out of bed in the morning is typically a real desire to go out and make a difference in the world, to really go on work on problems that matter to somebody in the world. And that sense of mattering to someone in the world may be in a business context, maybe in a societal context, maybe in a clinical context. So it doesn't always mean a corporate setting, but somewhere out there in the world has a problem that we can then address with mathematics, because me and my colleagues typically are really interested in mathematics, and we want to, though, do mathematics that has purpose, that has meaning and application. So we work through a process that we call modelling, of taking those real-world problems, which typically come to us as words, as descriptions, as discussions, often from people who aren't engineers. So those people don't always speak maths. And we go through a translation process, and that idea of translation is much like you would have with a spoken language. So if you speak French or German or Spanish or Maori, and you want to go from that language to English, there is a sense of translation. So what I do involves translating something that's given to me in English, and key step is translating it to mathematics. Now the catch with that is, even though I'm kind of good at mathematics, typically when you take a really difficult real-world problem like how much geothermal steam would come out of a well if I drilled it over there, that involves a whole lot of mathematical statements that are too complicated for me to solve. At least to solve independently, scratching out an answer on pen and paper. I still like to do that stuff when I can, and there are times when it's perfectly appropriate, but the kind of mathematics that I have fun with, we've got some seats over to the right here, the kind of mathematics that I have fun with is mathematics that is too complicated to solve by hand, and I teach a computer to solve it. Okay, so to teach a computer how to do maths, then you can do a lot more maths if you can teach a computer to do it. So sometimes I joke to people about what a good day looks like. A good day is solving 1 million equations before breakfast because I've got my computer going. Okay, by that definition, today's not a good day, but I can give my computer the day off. So in building those computer-based solutions, you do need to be able typically to write some code to be able to program, or to use software, and we do both. So in the degree, we teach people to code right from the beginning. So I teach first-year coding right from day one. So to come into the degree, all you really need to know is to be able to browse the internet well enough to find your way to the lecture theatre and turn a computer on, and we go from there. So if you want to have a go at coding, there's some coding sessions in a lab underneath us on level 3. That has advertised times, but just ignore those times. Just say I sent you, drop in. We're rolling them on an ongoing basis where you can have a go at learning some coding online. It's definitely not intimidating and is actually great fun. So, if you like mathematics, and remember that if you're applying to engineering, mathematics and calculus will be what you need. The other NCEAs or Cambridge, we've got scope to be flexible on, but mathematics and calculus are required. But if you like mathematics and you want to apply it, then engineering science could be a real home for you. And it could be applied via an engineering science degree and via a biomedical engineering degree. So those 2 degrees have kind of a common heritage and a common mindset, but obviously slightly different vision around application. So in general, what life would look like if you came and studied with us is in both degrees, engineering, science and biomedical, you would be learning mathematics. You would learn more mathematics in this degree than any other engineering degree. So you do mathematics classes right throughout. You do classes in computing, so you would typically learn a couple of different computer languages on your way through, languages like C and Python. You learn some relevant commercial software packages. And then in the engineering science degree, you would learn a particular style of mathematics called operations research, which is about doing things better, faster, cheaper. It's about optimizing things. So optimizing things might be, in terms of doing something better, faster, or cheaper, might be an example, for instance, working for Air New Zealand. We've had a long relationship with Air New Zealand, so if you've flown Air New Zealand, you've actually been touched by work engineering science does. They have a whole team of our people out at their base. And what those people do is optimize the crew rosters, because I don't want to say to a pilot, hey, fly that big plane to Los Angeles, have a cup of coffee, turn around and come home. Unsafe, union says no, plenty of reasons why you can't do that. But you also don't want to say to the pilot, hey, fly to Los Angeles, sit around in a hotel at 10 days at our expense, then turn around and come home when we've got a plane ready for you. That's not a great solution either. So we work at building computer systems that give Air New Zealand the best solution to map their crew onto their planes. And that solution, best, can be measured in any number of terms. Best can be measured in terms of what's the cheapest solution, what minimises the number of days that you've got crew on downtime where you may have to still pay them allowances, and best may be measured in what keeps the crew happy. Pilot may say, actually, I don't want to fly to Los Angeles this week, I'd prefer to go to Tokyo. So the crew are able to bid for rosters that work for them as people. In the continuum mechanics area of engineering science, we look at the mathematics of how things move. And those movements might be fluids or solids. So fluids, for example, modelling airflow through a wind turbine. How much energy can I get out? Airflow round the sail of an America's Cup yacht. We do a little bit of work for the America's Cup. In fact, one of our young graduates, 23-year-old, was the youngest performance engineer of any America's Cup team, and her number crunching and made a lot of the case to support the idea that we had guys on bikes. Instead of guys grinding with their arms, we had guys grinding using their legs. And she looked at the aerodynamics of how that was all going to work, built computer models to support the case that, hey, New Zealand's going to go and do something different. So that all fits in the area of continuum mechanics, fluids and solids. If you're in bioengineering, then you would typically delete out the operations research content and put in biology and physiology in classes with other students who may be up at the medical school. So I'm going to frame a lot of the rest of the talk around questions. We're driven by real problems, we ask a lot of questions. So I've got a whole lot of questions that ask, can we do certain things? Certain things that matter in corporates, in science, in the world in general. So for instance, can we design wind turbines to be more resilient to extreme events? So a lot of us at the faculty have an interest in renewable energy. We want to find ways for the world to transition. So wind turbine reliability is quite a big deal, because if you have strong gusts of wind, you wear everything out and you shorten the turbine life. So on this next slide, I have a simulation that one of our staff and some of our students have worked on. You have a row of wind turbines in the front, a wind gust coming through, and the colours represent the wind velocities. And from there you can back into the loads on the turbines and the impact that that's having maintenance-wise. In a totally different domain, but using the same kind of thinking about how fluids move, we have another colleague who looks at swimming microbes in terms of bacteria and other things. So a biological application, actually within the engineering science degree, that has all sorts of applications in terms of technology and in terms of just fundamental understanding of biology in general. So swarms of microbes have all sorts of really interesting dynamics because of the scale of microbes being very small. If you're very small, then swimming through a suspension like water, the water actually behaves like it's very, very viscous. So the microbes tend to cluster together in very important patterns. And that, if you understand that motion, then you can build sort of microfluidic devices. In the biomedical degree, can we change the way we walk to reduce the onset of knee arthritis? I'm getting sort of middle-aged and kind of old and creaky, and I would love to know if there were things in my gait I could change. Maybe I shouldn't be rolling my feet so much. Maybe I shouldn't run so much. Yeah, actually, no, I don't run so much anymore. We've already tested that that's kind of hard on your joints. So in terms of understanding those loads on the body, there's a stand on the sport and entertainment area where you can see some of the sensors that the team have built, where there's now a lot of sensing capability that can be deployed at almost commodity level, because most of us have actually incredible amounts of sensing technology in our phones in terms of accelerometers and other things. So this phone knows where it is, it knows if I've turned it upside down, it knows if I threw it on the floor. So you can integrate that sensing into clothing, into devices, and start to give feedback to someone in terms of sort of therapeutic applications about the loads on their body. We can also take a look forward to the future to say, can we get better outcomes from orthopaedic surgery? I've had a few orthopaedic surgeries. I don't recommend it as fun. Good outcomes are really important. And good outcomes, we believe, in the future are going to revolve around really customised, personalised medicine. So if, when my hip joint finally wears out because of my dodgy gait, I need a hip replacement, I would like that joint to be personalised to me, to the geometry of my body. So now what the team are doing is looking at taking individual patient MRI scans, building that into a computerised version of a particular patient, performing virtual surgeries so the surgeon can map out and design what is the best shape of that implant for that particular patient. In the running domain, our sensors for understanding loads on the body from running and tibial fatigue. So the tibia is your shin bone. So if anyone's ever had shin splints, you would know that that is something you want to avoid. How could we avoid that? Well, again, adding a little bit of sensing. So at the sport and entertainment stand, they've got sensors on little straps that you strap to the front of your shin. And when you strap them to your shin, you can then keep track of all the loads from your foot meeting the pavement. So the green on the right-hand side there is a shin bone. The colours represent strain or the amount of deformation in the bone. And that sensor can then talk to an app on your phone or your iPad to say, hey, you've been doing a bit too much running this week, you've loaded up your bones with too much stress and strain, you're getting into the danger zone for a stress fracture, let's back off your training before you get into the pain and issues involved with actually fractures. And the credit on this, by the way, is to a Part 4 or a final year student. So this is work that came out of a final year student project. So every degree has a final year project where 25% of your final year is dedicated to a particular question. So this was work that one student did and that has now gone along a whole pathway into a commercial product. 3D printing is another big technology that you'll hear about. 3D printing is going to change, what we can do, what we can design, what we can create. Ava here in the front row is always showing us amazing things that she's printed. So in the biomedical arena, we want to know, can we custom print joint replacements? So to do that, we need to be thinking not only of the geometry, but of the material. How do we design that material to handle the load? So in this example, we have an example of someone who has come through the undergraduate, the PhD, and is working with a commercial partner. We have companies come in off the street sometimes to the Bioengineering Institute to say, hey, we've got a problem, are you able to help? And typically we roll up our sleeves and we do. On the design side, in terms of new materials, we have people working with composite materials. So composite materials are things where you have a network of fibre, a network of resin that gives you lightweight but high strength. So that's important in a lot of applications, for instance, aircrafts, vehicles, yachts. But the process of making those materials needs to be understood. So we have people who look at the simulation of how does that resin move through the fibre network? How do you make sure the resin is going everywhere it needs to go so those materials really do have the strength that they are advertising? So you take that forward to think about designing things that are both light and efficient while still being safe. So if we've got these advanced materials that are light and strong, how do we design them into things that are safe? So we have a colleague who is interested in breaking stuff, crashing things into each other. So he's interested particularly in crashes involving water, for instance, high-speed yachts, and that kind of testing is difficult and expensive, so he looks at ways to do that testing on a computer. And then you can explore a much bigger universe of options. Going in a different direction in terms of sort of how mathematics and computing can help in the world. If you have ever been through diagnosis for breast cancer diagnosis requires a bunch of different scans. And in some of the scans you're standing up, some of them you're lying down, some of them you're on strange angles. And that geometry means that the scans each paint a slightly different story of how big the tumour is and where the tumour is. So how do you reconcile those to give the clinicians the best visibility? So we have people who look at the mechanics of the human body. How does the human body behave in different orientations when the body is being scanned? And then how can you reconcile that with MRIs and other sorts of images to give you the best possible understanding of the tumour before you operate. In the same sense of imaging, we go from, in the bioengineering degree, looking for breast cancer tumours which may be only a matter of a couple of millimetres, embedded in quite complex, elastic kind of structures, through to looking through rocks. I have a personal obsession with basically trying to develop X-ray vision and wanting to understand the ground between my feet, which is very stiff, very impermeable. So in the geothermal industry, we would love to be able to look kilometres below the ground to understand heat flows, mechanical deformations. So this image is from a colleague who is trying to image through geophysical methods where a geothermal system is, and to find that geothermal system below our feet, could be several kilometres below our feet, with no surface evidence. So by surface evidence, no hot springs, no steam coming out of the ground, nothing obvious that there's something special down there. So he reconciles different geological and geophysical information to try and come up with the Earth in the subsurface. He also has an interest in earthquakes. So David is on the environment booth and will show you some great simulations of earthquakes. We have people within the engineering science degree working in healthcare. So people working up at the hospital, they said, hey guys, you know how to do things better, faster, cheaper. And the health system is always going to have a finite amount of resourcing. No matter what flavour of government we have or any of that, there is always going to be a finite amount of resource in the health system. So we want to use it in the best possible way. So we've done simulations of, for instance, pathology scheduling to look at, this is kind of a virtual world of a pathology lab, to look at the inflows of the different kinds of tests to help them build staff rosters and those kinds of things so they can deliver the best possible service to their clinical clients. We've also done hospital simulations to say, can we understand orderly dispatch? So orderlies are the folks that transport patients around the hospital to say, hey, I'm in ward number 4 and I need to go to X-ray on the other side of the building, come and wheel me over there. So those orderlies move incredibly around the hospital. So how do you base them? How do you dispatch them? Who gets what job? So this is a snapshot of a simulation where you have An orderly base down in the bottom right, a queue of people waiting for work as orderlies. How do you choose what jobs they get? Another example that I am particularly proud of is around essentially data mining. And data mining is sometimes a phrase that does give you the chills. It's a concept that we have to think about a lot in the modern world. We all produce huge amounts of data with this digital footprint that we inevitably have. But we have a project where we're looking at mining public domain data, so death notices in the Herald, for example, and other statutory things, to reconnect Mori landowners with the land and with the dividends that come from their land. So Mori land is often owned by hundreds or even 1,000 individuals because of some of the treaty settlements and the family ownership, iwi ownership structures. And that land is often producing income in the form of a dividend, and it has to get back to its owners. And sometimes those records and those connections aren't there. So we have a project looking at data mining methods. So we're using our number crunching powers, and we're working with a trust in Taranaki to return $3 million in dividends that is owed to the Maori community and is making its way back to its rightful owners. In natural resources, we're also interested in water. Auckland has significant questions about water and its future. So we have people who can look at water networks and say, how do we manage those networks to perform well into our future? We also look at transport networks. So we have a demo on the transport stand thinking about how are we going to move in the future. And one of the challenges around moving around in the future is being energy efficient. So this next image is a slide, again, done by an undergraduate student, as many of the slides were, of Berlin. And what they were testing out in Berlin was, can we make the whole transport system more fuel efficient if we put different speeds in different places, different speed limits? Because if you drive around Auckland, you'll probably spend a lot of time accelerating and braking, and accelerating and braking. And that's not always the most efficient way to drive. So there are things that could be done at a system level to make it work better. So what would life look like if you enrolled in either a biomedical degree or an engineering science degree? First of all, the department has a really strong reputation for being very collegial. We have grown. We take now 70 engineering science students each year and 35 biomedical students. And those students come typically from the common first year engineering. Sometimes we do get a few transfers from medical and health science and other places, but the usual route is through the common first year, through a selection process. Once you've been in the department for a week or so, we throw everyone on a bus, or actually 3 or 4 buses, and we go on a bit of road trip. So we go and meet some of the companies that you might be employed in and do a bit of team building. So these are examples of a challenge that a company runs for us, sort of an amazing race type challenge down in Rotorua. I'll finish up with a few quick examples of our graduates because I'm always interested in people and their stories and their journey. So Mori Leyland is fairly well known. She, among other things, is the only woman to have sailed for Team New Zealand. She sailed on one race in the challenge in San Diego. But more importantly, she was on the design team that helped design the yacht that won the race. And that was using these ideas of continuum mechanics, of thinking about fluids, thinking about stresses and strains. She then moved out of the world of sailing, took those problem-solving skills that she'd built, moved into management consulting, and ultimately into the executive level of Fonterra. She did leave Fonterra, however, recently. Another graduate, more recent, Taranaki Raj in 2012, went straight into the business world. So she looks at sort of operations in a business context, works alongside people who have commerce degrees, but really flourishes in that real problem-solving world with Ernst & Young. And they, as a company, they are very keen to hire engineers. They really enjoy them. Jared Wallis is another example. Jared is down at the waterfront at Southern Spas, designing high-performance sails, high-performance yachts, high-performance rigs. So he's got a very successful career down there as a design engineer. And he brings both strands of the degree together, the optimization side and the mechanics side. Kim Noakes is one of many high-performance sports people we have had with us. That's her in her Black Sticks uniform. She went to the Olympics for New Zealand in hockey. She's a biomedical student who initially was working with clinicians around understanding the pelvic floor region, worked on clinical modelling there, and after a while she's moved into bioinformatics software overseas. Karen Wilcox was always my pick to be the first New Zealander in space. That's her in the Vomit Comet. And she is a professor of aeronautics and astronautics at MIT, although actually since I set this slideshow up, I forgot that she has moved to a new role in the University of Texas at Austin. And she uses mathematics and computation to look at design in the aeronautics and aerospace industries. What will the next generation of aircraft look like, or spacecraft? Matthew Lim is a biomedical student and is an example of a student who's working with the sort of startup culture that the Bioinstitute is building. So the Bioinstitute has some really challenging questions about understanding how the entire human body works, and that often means they need to measure stuff and there's no gear to measure it, so they just go and design it and invent it and find ways to do it. So Matthew is was employed at telemetry research. Telemetry research essentially uses Bluetooth in the lab. So the same Bluetooth that you have in your phone, telemetry research deploy that in a clinical research setting where if you want to monitor a lab animal and want to monitor nerve signals, for example, you can put a little sensor in your lab animal, your rat or your rabbit, but then you don't want your sensor to need cables so your animal is tethered to something. You want your animal to be able to roam free and do what it does. So their solution was you basically get your lab animal equipped with Bluetooth in a biocompatible way, and that technology is now in 25 countries worldwide. Ian Kim is another biomedical engineer, again very innovative, has ended up in Silicon Valley looking at the cardiac arena in terms of understanding the heart and the flows in the heart, the opportunities for sort of technical innovation around cardiac monitoring. And then the last graduate that I'll profile is Virginis Kumar, who's working for Fisher & Paykel Healthcare. Fisher & Paykel Healthcare are a Kiwi-based company, but they're exporting to the world. They have a very strong R&D division out in Auckland. And they look, a lot of their medical products is around breathing, whether it's consumer product for people who have sleep apnea, so they have breathing troubles when they're sleeping, or more advanced products for people who are intubated and are on life support systems. So he works in design of product with them. So I've already mentioned the coding workshops downstairs on level 3. Drop by, have a go. Don't be intimidated if you've never coded before. It shouldn't turn you off. And if you want to find out a little more about us, our official website is des.auckland, and our Facebook feed there is a little bit more informal, a little bit more fun, gives you an idea of student life. So feel free to ask questions either in a group or one-on-one. So thank you.